friends, myself Rupali Paliwal. Today we see the Riemann integration. This is the second lecture series on a Riemann integration. In first lecture series, we see the Riemann sum. In this lecture series, we see lower and upper integrals, Riemann integral or R integral, and theorems based on Riemann integral. Now we see lower and upper integrals. Suppose f be a bounded function defined on the interval closed interval of ab. The supremum of LPF is called the lower R integral of f or lower Riemann integral of f on closed interval ab, and it is denoted by integration from a bar to b f of x dx or integration from a bar to b f. This is the notation of lower integral. That is, integration from a bar to b f of x dx is equals to supremum of LPF for all partition P of closed interval AB. That is, lower integral means what? The supremum of lower Riemann sum of the f of x with respect to the partition P for all partition P. Now, the infimum of UPF is called the upper R integral of f or upper Riemann integral of f on closed interval AB, and it is denoted by integration from a to b bar f of x dx or integration from a to b bar f. That is, integration from a to b bar f of x dx is equals to the infimum of UPF for all partition P of closed interval AB. That is, infimum of upper Riemann sum of f of x with respect to the partition for all partition P is called the upper Riemann integral. This is the notation of upper Riemann integral. Now we see the Riemann integral or R integral. Suppose f be a bounded function defined on the bounded interval closed interval AB, then f is Riemann integrable on closed interval AB if and only if integration from a bar to b f is equals to integration from a to b bar f. That is, lower integral is equal to the upper integral. Then we call f is a Riemann integral. Their common value is called R integral of f on closed interval AB, and it is denoted by integration from a to b f. That is, integration from a bar to b f is equals to integration from a to b bar f is equals to the integration from a to b f. That is, upper integral is equals to the lower integral. Then we see that the f is a Riemann integral. We see the theorem. If p star is a finer than p or refinement of p, then we have to prove first LP star f is greater than or equal to LPF, and second one is the UP star f is less than or equal to UPF. That means P star is a refinement of P, then we have to prove lower Riemann sum of f of x with respect to the partition P star is greater than or equal to lower Riemann sum of f of x with respect to the partition P, and second one is the upper Riemann sum of f of x with respect to the partition P star is less than or equals to the upper Riemann sum of f of x with respect to the partition P. Here P star is a refinement of P. Now let's see the proof. Let P is equals to the set A is equals to x0 less than x1 strictly less than x2 up to strictly less than xn is equals to B. B any partition of closed interval AB. Let P star is a refinement of P. हमने यहाँ ले लिया है एक पार्टीशन ऑफ क्लोज इंटरवल ऑफ ए बी का एनी पार्टीशन लिया, एंड पी स्टार इज अ रिफाइनमेंट ऑफ पी. दैट मीन्स सपोज पी स्टार कंटेन्स just one element more than p, say neta. Here p star is a refinement of p, then we consider p star contains just one element more than p, say neta. Let neta lies in at subinterval. Let neta lies in at subinterval. Let's see here. This is the real line. On here here is a A and here is a B, close interval of AB, and this is the at sub-interval of closed interval of AB. This is the xi minus 1 and this is the xi. This is the ith sub-interval in which neta is lies. That is, neta lies in the ith sub-interval. Here is the neta. Now let u1, u2 and small mi with a lower bounds on closed interval of xi minus 1 to neta, closed interval of neta to xi, and closed interval of xi minus 1 to xi respectively. That is, u1 is a lower bound of that interval, u2 is a lower bound of that interval, and small mi is the lower bound of that interval. Here, this is the first interval, this is the second, and this is the whole third interval. Then small mi is less than or equal to u1 and small mi is less than or equal to u2 out of this sub-interval. Obviously, this is the first closed interval of xi minus 1 to neta. Here lower bound is a u1, that is, here is a u1. Now second closed interval is a neta, closed interval of neta to xi, and u2 is the lower bound of that interval, that is, u2 is here, and small mi is the lower bound of that whole interval xi minus 1 to xi, that is, and mi is the lower bound, that is, here is a mi. That means small mi is less than or equal to u1 and small mi is less than or equal to u2. Obviously, consider LP star f minus LPF. We have to prove first is a LP star f is greater than or equal to LPF, but we consider LP star f minus LPF is equals to u1 into neta minus xi minus 1 plus u2 into xi minus neta minus mi into xi minus xi minus 1. That means a lower bound of that interval, that is u1 into the length of that interval. Next, plus u2, this is the lower bound of that interval, u2 into length of that interval, because LP star f means lower Riemann sum of f of x with respect to the partition p star. This is our partition p star in which one more element contained, that is neta. This is the partition p star. u1 is the lower bound of that interval, closed interval of xi minus 1 to neta, and u2 is the lower bound of this. And our Riemann sum, by definition of Riemann sum, what? Lower bound into the length of that interval. This is the lower bound of that interval, and length of that interval is the neta minus xi minus 1. This is the u1 into neta minus xi minus 1 plus u2 into xi minus neta. That is u2 into length of that interval xi minus neta minus, here minus is a LPF, that is lower Riemann sum of f of x with respect to the partition p. Here we consider the ith sub-interval, that is this xi minus 1 to xi, and lower bound of this interval is a small mi. That means minus small mi into xi minus 1. Small mi, that is lower bound into the length of interval, that interval xi minus 1 to xi, length of that interval is a xi minus 1, that is small mi into xi minus 1, which is equal to u1 into neta minus xi minus 1 plus u2 into xi minus neta, that is as it is, minus mi into xi minus neta plus neta minus xi minus 1. Here we add this neta plus neta and minus neta. Then next line, u1 into neta minus xi minus 1 plus u2 into xi minus neta minus mi into xi minus neta minus small mi into neta minus xi minus 1. Here we separate that interval and multiply minus mi to both. Here we separate this xi minus neta, this is the one bracket, this is in the one bracket, plus into neta minus xi minus 1, and then multiply minus mi to both bracket, that is minus mi into xi minus neta minus small mi into neta minus xi. That is, we expand that bracket. Now, therefore, LP star f minus LP f is equals to the bracket, in the first bracket u1 minus a small mi into the second bracket neta minus xi minus 1 plus u2 minus small mi into xi minus neta. From this term here, from these two terms, that is u1 into neta minus xi minus 1 minus small mi into neta minus xi minus 1. From these two terms, this term is a common in the bracket neta minus xi minus 1, and here also neta minus xi minus 1. This term is a common. Then we get this common. Then we have into u1 minus small mi, that is a u1 minus small mi. Similarly, from these two terms, this term is a common xi minus neta and xi minus neta. Then we get u2 minus small mi into the bracket xi minus neta. This is the u2 minus small mi into the bracket xi minus neta. Therefore, LP star f minus LPf is greater than or equals to 0. How? As small mi is less than or equal to u1, this implies u1 minus small mi is greater than or is equals to 0. And small mi is less than or equal to u2, this implies u2 minus small mi is greater than or is equal to 0. As we know, here is a small mi is less than or equal to u1 and small mi is less than or equal to u2. From these two terms, we get these two terms, u1 minus small mi is greater than or equal to 0 and u2 minus small mi is greater than or equal to 0. That means u1 minus small mi is greater than or is equal to 0, and here also u2 minus small mi is greater than or is equals to 0. Then whole that term is greater than or is equals to 0, and that term is equals to this LP star f minus LPf. That is, this term is also greater than or is equal to 0. That means we get LP star f minus LPf is greater than or is equal to 0. Therefore, LP star f is greater than or is equals to LPf. That is the lower Riemann sum of f of x with respect to the partition or with respect to the refinement p star is greater than or is equals to the LPf. That is lower Riemann sum of f of x with respect to the partition p. Similarly, we can prove up star f is less than or equal to upf. Now next we see the Darboux theorem. Here we have only statement. There is only statement. We see the only statement. If f is a bounded function on closed interval ab, then to epsilon greater than 0, there corresponds delta greater than 0, such that first is a upf is strictly less than integration from a to b bar f of x dx plus epsilon, and second one is the LPf is strictly greater than integration from a bar to b f dx minus epsilon. This is the upper integral and this is the lower integral minus epsilon for every partition p of closed interval ab with norm v of p is less than delta. This is the Darboux theorem. There is only statement. This statement is used in the next theorem. The next theorem is a necessary and sufficient condition for integrability of a function. The statement of that necessary and sufficient condition is: the necessary and sufficient condition for integrability of a function f over closed interval ab is that for given epsilon greater than 0, there exists delta greater than 0, such that upf minus lpf is strictly less than epsilon for all p with a mu of p is less than delta. That means f is integrable if the function f is integrable, then upf is minus if f is integrable, then upf minus lpf is strictly less than epsilon, and if upf minus lpf is less than or epsilon, then f is a integrable. Then we say the f is a integrable. Now first we see the proof. Now first we see the necessary condition. For necessary condition, we suppose that f is a integrable. Let f belongs to R of closed interval ab. That means f is a Riemann integrable. then we know f is Riemann integrable, then their common value is this integration from a bar to b f is equals to integration from a to b bar f is equals to integration from a to b f. That is upper integral is equals to lower integral is equals to the integration from a to b f. This is the Riemann definition. This is from the definition of Riemann integrable. Now next one is the Darboux theorem. By Darboux theorem we have UPF is strictly less than integration from a to b bar f dx plus epsilon by 2. Here we choose epsilon by 2 because epsilon is strictly greater than 0. That is, epsilon is any value which is strictly greater than 0. Here we choose epsilon by 2. And LPF is strictly greater than integration from a bar to b f dx minus epsilon by 2. This is the by Darboux theorem. This is Darboux theorem. There is we choose epsilon instead of, there we choose epsilon by 2 instead of epsilon. Here, therefore, minus LPF is strictly less than minus integration from a bar to b f dx plus epsilon by 2. Multiply negative sign. We multiply on both sides by negative sign. Then here the inequality is also changed. Here strictly greater than, then inequality change is a strictly less than. Now consider UPF minus LPF. We have to prove UPF minus LPF is less than epsilon. Then we consider the LHS, that is UPF minus LPF. Then we put the value of UPF, the UPF from equation 2. We get UPF is strictly less than integration from a to b bar f dx plus epsilon by 2. This value we put here. That means here strictly less than integration from a to b bar f of x dx plus epsilon by 2 minus LPF. Minus LPF from equation 3 minus LPF is a strictly less than minus integration from a bar to b f dx plus epsilon by 2. Then we put directly value of minus LPF is a this minus integration, that is minus integration from a bar to b f dx plus epsilon by 2. Here from equation 1 this is strictly less than integration from a to b f plus epsilon by 2 minus integration from a to b f plus epsilon by 2. This is from equation 1. Why? Because upper integral is equals to lower integral, lower integral is equals to the upper integral is equals to integration from a to b f. Therefore we get this is the integration from a to b f, and this is the minus integration of a to b f. This one is a cancel. Then we get epsilon by 2 plus epsilon by 2, that is 2 epsilon by 2. This is strictly less than epsilon. We prove the first part, necessary part. This is the UPF minus LPF is strictly less than epsilon. Now we prove the sufficient condition. Conversely, suppose that for each epsilon greater than 0 there exists a delta greater than 0 such that for all partition P with mu of P is less than delta, UPF minus LPF is strictly less than epsilon. Now we suppose conversely that UPF minus LPF is strictly less than epsilon. This is equation number 4. Also we have LPF is less than or equals to integration from a bar to b f dx is less than or equal to a to b bar f dx is less than or equal to UPF. From this we get integration from a to b bar f dx minus integration from a bar to b f dx is less than or equal to UPF minus LPF. From this step we get this integration from a to b, that is this integration from a to b bar f dx minus integration from a bar to b f dx, this one is less than or equal to UPF minus LPF. And from equation 4 UPF minus LPF is less than epsilon. This is the value of UPF minus LPF strictly less than epsilon from equation 4. Therefore, integration from a to b bar f dx minus integration from a bar to b f dx is equals to 0. How this will come? Here the reason integration from a bar to b bar f dx minus integration from a bar to b f dx is strictly less than epsilon. This is this step, that is 0 is strictly greater than that is 0 is strictly less than epsilon. Since epsilon is strictly greater than 0, here epsilon is strictly greater than 0, that is epsilon is strictly greater than 0, then we get the integration from a to b bar f dx minus integration from a to b f dx is equals to 0, because we compare that two steps, then we get that integral or that step is equals to 0. Therefore, integration from a to b bar f dx is equals to integration from a bar to b f dx. That means, therefore, f is a integrable function. Upper integral is equals to lower integral. We get the upper integral is equals to lower integral. Therefore, f is a integrable function.